and Technological Association Thailand, or COSTAT. In this seminar, due to the COVID-19 pandemics affecting the world, so we will be organized in the online form. First of all, I would like to invite Major General Dr. Chainalong Cherchu to deliver his report speech of this seminar. Please give your hand to.
Thank you very much. Good afternoon, everyone. I think that with this situation of the COVID pandemic, I hope everyone is safe from this meeting and go back home with happiness. COSTAT TU Delft assembled Team Thailand, Thai PBS, and the UNDP have organized international seminar on satellite subsidence and sea level data, assimilation for mean high water line assessment in the Bangkok area. I would like to report about this research project to acknowledge the following objectives. Develop a data assimilation approach to evaluation of subsidence resulting from groundwater extraction in an area affected by sea level change. First, to monitor subsidence through in situ leveling, GPS observations, and INSA analysis. Second, monitor sea level changes through Thai gauges and satellite altimetry. Third, measure groundwater levels in observation wells. Fourth, combine number of numerical model with observation to evaluate expected changes of the Thai coastline. And last, ultimately, this system will help prevention and mitigation of flood hazard. I would like to take this opportunity to thank the Ministry of Higher Education, Science and Innovation, and for everyone, especially Thai PBS, to support this seminar. Last but not least, I would like to take this opportunity to cordially invite Associate Professor Dr. Pasis Lord Thilapung to give the opening speech, please. Thank you.
Good morning. I think good morning for Netherlands and good afternoon, Thailand, right? President of COSTAT, Professor Femka Wasipel, Mr. Wim Simons, and ladies and gentlemen. On behalf of the Permanent Secretary, I would like to thank you, COSTAT, Dr. Femka Wasipel, the project leader, Mr. Wim Simons of Delft University of Technologies, and of course, Team Thailand, to organize this international seminar on satellite subsidence and sea level data assimilation for mean high water line assessment in the Bangkok area. We all know that Netherlands has been regarded as expert in dealing with water-related crises and challenges. We hope that this cooperation between the two countries will provide a platform for relevant organizations and stakeholders from both sides to maximize the outcome of this activity, to enhance partnership, to initiate series of follow-up activities, and continue to work for concrete mutual benefits in the long run. We also hope that the success of this project will bear fruit not in the too distant future, which requires sustained and strong commitments from all stakeholders from both countries. As a representative of all Bangkokians, we would like to thank you, all of you here in advance, for working together, and we strongly hope that the outcomes of this activity will be a big push for all concerned stakeholders to proactively work together, and hopefully we can protect our Bangkok from being the underwater city. Thank you very much.
Thank you very much, Associate Professor Dr. Pasit Lorthiraphong, for honoring us to give the opening remarks to us. Now, I think that you are very interested now in the topics that will be given by our speakers. Okay. Then I would like to invite our first speaker. Okay. Dr. Fremke Wassopoo, and the topics that he will be presented is the project overview. Dr. Fremke Wassopoo from Delft University of Technology. Please give your hand to him.
Phayathai, apologies for pronouncing your name, and also many thanks, Professor Lorthiraphong, for the very kind opening words. And I would really like to thank the director of Costas for hosting us and making it possible to organize this seminar. I will now try to share my screen, and this may take a minute. Can you confirm in the chat that you can now see my screen? Thank you very much. Then I will start my presentation. And the title of the project is Satellite Subsidence and Sea Level Data Assimilation for Mean High Water Line Assessment in the Bangkok area. This is a lot of words, but I'll get into the more details in the course of this presentation, which will be an introduction to the speakers in the rest of the Thai afternoon and Dutch morning. The project is a truly international collaboration of TU Delft with the partners in Thailand, as well as another partner in the Netherlands and a partner in Leeds, and I will introduce them to you in a moment. But first, the agenda of my lecture today. After my welcome, I will introduce the participating institutes and the team, the people really doing the actual work. And I will give a short impression of how the coastal region in Bangkok is changing at the moment. From this situation, we formulated our research objective, which I will then explain, and I'll take some time to go into data assimilation and integration, because that's the key novel aspect of this project. As I mentioned before, a lot of institutes are involved in a lot of different data types. For each of the data types, there will be different speakers who know more about the data than I do, and I will only briefly introduce their talks. I will also mention the numerical models that we will use in the data assimilation. I'll give a timeline of the project and our outlook into the near future. Please, on this slide, see all the people that are currently involved, and there may be more to come in this work. We're very happy to collaborate with Anoushka Alpert, who's done a lot of work on the subsidence from Kasetsart University. And Captain Sommert has been instrumental in setting up the logistics and the relations and the data access with the Royal Thai Naval Academy. We're also grateful to Dr. Somsak Patanaprida of the Department of Mineral Resources, who has helped us to access to data. And recently, Ms. Chadaporn Buzarakum has provided us access with very useful groundwater data. From University of Leeds, we have the pleasure of collaborating with Professor Dr. Andy Hooper and his postdoc, Dr. Milan Lazeki, who have provided us with some very recent INSAR results. And then at the Faculty of Aerospace Engineering, we have both Wim Siemens and Mark Naye contributing with us on GNNS and altimetry, and both of them will be speaking later on. Dr. M.A. Slangen unfortunately could not join us today, but she is providing the oceanographic input. Professor Mark Bakker, who is also not there today, is supervising the hydrological part. And in our midst today as well, and she will be presenting later on in the seminar, is Jenny Suntarn-Rengsen. And she is currently working on her PhD project on this topic, and she will be supervised by many of the people above, but I will supervise her in the aspect of data assimilation. On the right, you see the logos of the different participating institutes. Moving on, and I just took the pictures of those people where I had pictures available and who I knew would be there today and presenting today. So Andy Hooper could unfortunately not be there in University of Leeds. Mark could not be there. Milan, working with Andy, will not join us today, and neither will MA. But the other people on this slide will all contribute, and you will see them presenting later today. I'm extremely pleased to have such a rich and international team working with me on this project. But let's start on the topic of our research. We have a changing coastal zone around the Bangkok city. And I took this picture from a news article in the Asian Post, and it illustrates how severe the sinking of Bangkok is at the moment and how important it is to know how much the land will subside and how we can protect Bangkok for unnecessary floods. We realize that this is all related to the global sea level rise, which is related to climate change. And it is not only that which is contributing to the coastal area changing, but also the fact that the ground in Thailand is subsiding. And there are several processes contributing to that. First of all, the extraction of groundwater from the aquifers under Bangkok is causing subsidence in a deeper subsurface. At the same time, land changes such as erosion, both from the river and from the coast, will also contribute to this changing land. And not mentioned in this slide, but the foundations of buildings then also becomes very important on how the subsidence is experienced in the city of Bangkok. I think you will all agree that better monitoring, but also the integration of all the data that we have available will eventually lead to a better protection. Now, how does the area of Bangkok look underneath our feet? These are two graphs that I took from literature, which nicely illustrates how below the river there are multiple water-bearing rocks, aquifers, that can be used for groundwater supply. And some of these, most notably the PD, the red one here, NL, I don't dare to pronounce it, the green one, and the The blue one, which are indicated in these numbers, they are being used for this groundwater pumping, and that will then result in a change of stress level in the subsurface, which will eventually lead to subsidence of the city of Bangkok. A lot of work has been done already on knowing the geology, on knowing the water systems, and we will, in our project, we will build on this knowledge by carefully looking at what is known about those systems, and we will try to model these. That brings me to the overall project objective, which will be to develop a data assimilation approach. So we will integrate data with models for the evaluation of subsidence resulting from groundwater extraction in an area that is severely affected by sea level change. This means we will monitor subsidence, and for that we use our expertise in satellite data combined with the available in situ leveling data that are available in this region. We will monitor the sea level changes through the local tide gauges that are installed in your area, but combining this with satellite altimetry, where TU Delft has a clear experience in processing. We will measure groundwater levels in observation wells and make use of historic data sets. And we will combine this very rich data set with a set of numerical models where we can then really monitor, best monitor what is expected in the future. So not only look backwards to the data where we have them, but using those models, we can create scenarios of what will happen in future. And ultimately, we think this will strongly help Bangkok to prevent its beautiful city and to mitigate any hazards that may occur. I tried to depict the project in a cartoon, in a graph, where you can see how the collection of all those different data sets will help us to better monitor exactly where the position of this interface between the sea and the land will happen. So that's referred to as the mean high water line variation that you see here. To monitor the position of the land, we will have Gnns stations, benchmarks, which are monitored by a range of satellites orbiting, GPS satellites orbiting the Earth. In addition to that, the combination of synthetic aperture radar images will help us to monitor the downward motion of the Earth as well. And on the sea side, we will measure the sea level relative to a reference ellipsoid from the satellite altimetry, and we can combine that with local relative sea level observations from tide gauges. Later on, Mark Naye will explain more about this concept. By combining all those different data sets, both in situ in the location of Bangkok and from satellites, we can get a much better description of the system than from the data alone. And what is really new in this project is that we will combine this with numerical models. And that's a concept known as data assimilation. Let me take some time to explain you how this data assimilation works. Data assimilation is a technique that comes from meteorology, from weather prediction, where we typically run a forward model, let's say of the temperature in a place, and we run it forward until we have a prediction. Then at that moment, let's suppose that we have an observation of this temperature, and the observation tells us it's a lower temperature. We can then adjust the variables in this model, so the temperature of the model, but sometimes also certain parameters in the model, and we come up with a new condition for the model that's shown here. And with this new condition, this new initial condition for the model, we can run the model again, which would hopefully lead to a better forecast. When we then have new observations, we can correct the model again. And this is how we continue in time, eventually leading to forecasts which are closer to the observations. Not only are the observations then closer to the forecast, we also have a very rigorous way of dealing with uncertainties in the data. This becomes especially important when you start to combine data from many different data sources. And of course, the errors in satellite data can be very different, both in their spatial nature and in their absolute amplitude, than errors that we have in situ places. Also, we need to take into account that not all models are perfect, that the models have been based on assumptions on the physics, that they've been based on assumptions on certain parameters, and that those parameters and assumptions and the description of the state of the ocean and the land may not be fully accurate. Now, our probabilistic researcher Bayes has posed Bayes' theorem, which we can use with a very elegant, simple equation to describe the probability of a model state occurring given the data, and it then simply becomes a multiplication of the likelihood of the data. So how likely is it that we measure a certain land or ocean state times a prior probability of a model state. And that's the mathematical basis of the technique that we refer to as data assimilation, which we will use in this project. After this quite technical description, I will now move to the different data types that we will introduce in our project. And I start with the Gnns positioning satellites, which will make use of the GPS constellation. There are a number of local GPS stations, which we are very grateful for our Thai collaborators that we've been able to install these and maintain them in close collaboration. And they are then the data from these stations are then being processed with the latest and greatest GPS software, partly developed at Delft University of Technology. This allows us to monitor positions in the neighborhood of Bangkok, as you see here, with millimeter accuracy. I will leave further details for William Simons to explain after my talk, but this is one of the main data sets that we will be using in our project. In addition to these data sets, we will also use the sea level data available. I already mentioned the availability of tide gauge measurements, which we have in certain locations in the Gulf of Thailand. And some of those will be used to calibrate the radar altimeter data. And this graph, which will be explained by Mark Naye later today, gives how those tide gauges really complement the satellite data and how from that we can derive not only relative sea level changes, but also absolute sea level changes. I mentioned that we want to combine data with models, and the models that we will use here will come from the IPCC analysis. A little bit more on that later in this presentation. A number of papers have already been published on the combination of those data, and this is a recent one, I think from 2019, where there was already a very strong collaboration between Delft and Thailand, and I'm very pleased to see this collaboration continue. So we've now discussed the GNSS positioning observations and the sea level observations, but what is also important is to know the spatial distributions of the subsidence, of the downward motion of the Bangkok area. And for that, we will rely heavily on the analysis of Anuvrouw Aupert, who will give a presentation later today, and of the expertise of Professor Andy Hooper and his postdoc Milan Lejek. They've provided us very recently with this nice overview of the Bangkok area, where you see this region. If I'm not mistaken, this is where the city of Bangkok lies, and earlier work by Anuphav Alpet already demonstrated how parts of this city have been subsiding. Now later on, Anuphav will explain to you that some of this subsidence has stabilized and some of the subsidence is now occurring in other places. So it's extremely interesting to see how this subsidence is evaluating over time. One of the challenges that we're facing when collecting all those different data is that, of course, we would like to tie the data to the model in a certain period where we have the different data types available. And for INSAR, we don't always have a continuous data set, and we may have some images of certain periods, but not of others. So we're now collectively looking at what would be the best periods to deal with those data. But already before creating this database, our PhD student, Jenny Sunturn-Rangsen, has started looking at the groundwater heads, which are kindly provided to us by the Department of Groundwater Resources. She has identified a number of locations where we can clearly see how the water level has decreased as a result of pumping, and other locations where they seem to remain stable. We would also like to monitor rainfall and evaporation where that's available. If we don't have local observations, we can always use the reanalysis of global data sets. But I think at the airport in the Bangkok region, there's a good collection of meteorological data. In addition to that, we may also include the water levels of the river Phayathai to really know what is going on in the hydrological system of this area. More on this will follow in a presentation of Jenny later on today. I already mentioned it. There are many different data types, and I realize that you cannot read this probably, but that's okay. It's really about the message that some data are available for historic periods, but not for present day. And other data sets only started present day or recently and have not been available in earlier years. So one of the challenges we're facing now is to really combine those data sets, but that's also where the data assimilation can help us, because in periods where we don't have the data or where we have less data, we can rely on the models to fill in the gaps. I mentioned the models, and these are the two main types of models that we will use. First, there is the PASTAS software, which is allowing us to create time series analysis from the data. So it's a data-driven model, which has been developed by Professor Mark Bakker at our university. It's a relatively straightforward model to use, and it's very flexible in how we set it up and what we include in the model. In addition to that, for the sea level changes, we will use the state-of-the-art models of the IPCC, the International Panel for Climate Change Consortium, where there is a coupled model into comparison project where our colleague MHESI Lange is involved. The new results of this intercomparison project will be shared today. There will be a big press release of the IPCC report, and that's the exact reason why MA unfortunately could not be with us today, because she has to talk to the press. So we will use those models, and having MA in our team allows us to really use the models themselves, but also to include the uncertainties in the models and to create ensembles of model forecasts, which we can then use in the data assimilation. And eventually, those models, both the groundwater models from PASTAS and the ocean models, will be combined with both the local data and the satellite data. It will not surprise you that incorporating all those different aspects really ends up in a very complex interplay of different work packages and different tools. And it's almost too much for a single PhD student to integrate all of this. So that's why I'm very pleased to have all of our collaborating institutes helping in this project. At the moment, the focus is really on the subsidence itself and how this relates to the groundwater pumping. And Jenny will tell a little bit more about that later today, where little by little, we will start to incorporate not only the groundwater data in situ, but also the satellite data. We will start by studying historical data. I mentioned here 1994 to 2019, but we even start before that to really understand the groundwater systems. And then as of next year, Jenny and with our colleagues will start to look more into the altimetry, satellite altimetry, the tide gauges, and combining that with the sea level estimates. Eventually, those green and blue parts of the work should help us to find a better mean high water line estimate, first for the past, and then eventually also work with that same framework to look into the future and test what would be the consequence of certain groundwater pumping scenarios on the situation in Bangkok. This is the timeline as we thought of it when we submitted the proposal. And of course, we all realize the timelines cannot always take place the way we planned it. We were hoping that all of us would be present in Bangkok this summer and to really have a kickoff with you, but that didn't take place. But we do hope that at some point in the second year, we will be able to have another seminar like this, if not physical in Bangkok, then certainly via internet. And we then hope to close the project off by another final seminar in the year 2025 or 2024 if we're early. In the end, the idea is that all of this work will result in the PhD thesis of Jenny. But in addition to this, I think there will be a lot of scientific publications coming out from the project. And I sincerely hope that it will strengthen our collaboration. On the shorter term, the outlook is that we will first construct a database and really see what is available already with the Thai institutes and what data do we have in our satellite data archives. And Jenny has already started on our first hydrological analysis for specific locations. We hope by the end of this year or early next year to construct a data assimilation framework where those data on subsidence and groundwater can be combined with the PASTAS modeling software to have a description of the subsidence in the Bangkok area. And then as of next year, we will start to bring in the sea level data analysis into the project. I already mentioned we sincerely hope that we can have another seminar and perhaps even a workshop in the next year. And in the years to follow, we will further develop towards a monitoring of the mean high water line analysis. I realize that this is my last slide, and with 27 minutes, I think I still have 3 minutes left. I'm not sure if there's a possibility to ask questions, but I sincerely like to thank you for your attention to this presentation.
Thank you very much, Dr. Femke Wososu. I'm sure that it will be very beneficial to Thailand, and the results of this research also will be useful for the researchers in Thailand. Okay, right. Next presentation, I would like to invite Mr. Wim Simon from TU Delft, and he will be given the lecture on the topics is Global Navigation Satellite Systems, GNSS observation to study vertical land motion in the Greater Bangkok. Please give your hands to Mr. Wim.
Sorry, so again, sorry. So good morning, everybody in Europe. Good morning, everybody. Good afternoon, everybody in Thailand and other parts in the world. So unfortunately, although it was not easy, I've been able to come to Thailand because I also had some other work we had to do. So at least I could be present. And today I'm going to talk to you about the main thing I'm doing, my own expertise, well, the measurements I do myself related to the global navigation satellite system. My work itself is actually embedded in monitoring tectonic and man-induced land deformation in Thailand using geodetic space techniques. So that's what I'm going to talk about a little bit in general, and then I'm going to go on, as I was introduced to, with the topic on the vertical land motion of Thailand. Okay, so the contents of the talk today is, I'm going to watch to the right because otherwise my eyesight is not good enough to read on the other terminal. So some history on the GNSS research activities in Thailand by myself and by my university, TU Delft. A summary of the space geodetic techniques. I will talk there a little bit more in depth about my own technique, GNSS. And I will briefly introduce the other techniques, but then they are later on by my colleague, Mark Naye, and also my other colleague, Thai colleague, Dr. Anapo, is going to talk to you in more detail on. Then, of course, vertical motion in Thailand, that's important to get from the measurements we are doing, especially if we talk about land subsidence. So the GPS can measure for us how much a point somewhere in Thailand is moving up. Well, that's not happening a lot lately, but mostly down. And we can get a very nice estimate about that over a long period, many years in time. I have to talk to you a little bit about tectonics, just to show you that also plays a role in there. Not that big for Bangkok, but still a little bit for the more southern, or more for the southern parts of Thailand. And then I'm going to show you some results we've done already for Phuket Island. Then I'm going to continue talk about GNSS stations in Bangkok. That's, of course, for this project what's going to be important. Some results we are doing, but of course, there are some results because we've been doing this for many, many years in other projects, and now we can use this data for this project, but we need to get some more data. I'll get to even try to come up with better results. The research activities, I don't want to go into detail, but what is important to know, the current ones, is that we ourselves, as TU Delft, are operating a number of those continuous GNSS stations. With the other satellite techniques, which my colleague will talk about later, the satellite measures to the Earth, and you get the data from the satellite as it is sent back. With the GPS or GNSS, which is the family name for all the systems, GPS has been most used because it has been around the longest. You have to collect the data yourself on the location where you want to know how much it is moving, in this case vertically, but also horizontally. So we have been having a couple stations there. The oldest one is already since 2005 in cooperation with the Royal Thai Survey Department. Now we have installed another one near a tide gauge. I will explain to you, we're not aware what a tide gauge is, very briefly. Mark will do as well later on. And then we have another stations, actually 2 stations in southern Thailand in Phuket. These are the stations we have ourselves been operating, but there are many more stations in Thailand from other government agencies. And in this project, fortunately, we'll be able to use and look in their data. They might not have as long time history as our own stations because we already started back long time to collect, but they will probably also be very useful. So we have cooperation for many years with universities like Chulalongkorn University, or Prince Songkhla University, or the Royal Thai Naval Academy with Captain Samart. So the 2004 earthquake was for us, for scientists, a big scientific interest because it's changed a lot. Also in motions, vertical, horizontal, but also from the geophysical viewpoint. It was it was the first earthquake so big that was ever been recorded with GPS stations. Because the latest one before in Chile was in the 60s. There were no GPS satellites back then. So this was the first time. And that gives us a big opportunity to study, because these motions, they tell something about how the Earth responds. If you can fit, like Femke already explained, if you can fit the data with the model or improve the model because of the data, you can also use it to predict for the future how certain motions will evolve. So that's quite important. Okay, so the other things, we will provide the PDF also to you so you can read in detail. But of course, the focus now is on the vertical motions, and that's for Bangkok in this project and also still in the south of Thailand. And then we combine this with the other satellite techniques. So the techniques themselves, which are being used, there are 4 actually. 3 of them are coming from using satellites. The first one, the GNSS, as I mentioned to you about, the Global Navigation Satellite System, which you all using also your phones, but we can get the accuracy at the millimeter level using specific scientific equipment. Then the other technique, the second one, is using a satellite. It's called the satellite altimetry. That's measuring the ocean height over a period of time. Then the next one is another satellite using radar, and we call it SAR, Synthetic Aperture Radar Interferometry satellite it is. And that one is showing us deformation in a certain area. So it takes radar images like, let's say, 30 by 30 kilometers. And in that area, by taking the same image from the satellite, of which we have to know very precise its position, but that's also something which is done. We actually also work on that ourselves. Then you can see how the images change. So the radar images will be different, and then you can see in the same image how certain areas are going up or down. So that's also very useful. And then the latest one, that's a traditional technique, the tide gauges. They are basically located at the coast or river mouths, and they measure the change of the sea level over a period of very long time. They were already installed more than 100 years ago. So they just know, then you measure the sea change over a long period of time. So these are actually the main 4 measurements direct. But then, of course, the groundwater, which Femke mentioned, is also an addition to there, which I also put there, and rainfall, temperature, and river data. So mine, I just go on to the next slide where I zoom in into the GNSS. Yeah, so that's basically the technique. It works for the user quite easy because you just have to record the satellites signals coming to you from space on the ground, where you place your antenna. You see on the right, you see there's the antenna on the RTSD base station. There the antenna collects the radio signals, and it's doing that the whole day, day in, day out, year in, year out, and then per day from that, we can estimate the position of that antenna. Nowadays, we can do it horizontally, actually, at the millimeter or below the millimeter level, and in the vertical, that's a little bit less because there are no satellites below us. We only can see the satellites up, coming from right to left. We still get a couple millimeter accuracy. So if you can do that for 5 years, 10 years, and keep the same station, it will tell you how that station is moving. And then the vertical, which is you see on the right panel, the evolution there tell you something about how the station is subsiding, in this case, at the rate. It's not too high, but it's still significant if it goes on, because the rate is higher, I think, for this station than the sea level rise was in the past. So if the station is moving downwards at a rate higher or equal or multiple times the sea level, actually then the land subsidence is the biggest threat, in combination, of course, with the sea level rise. Because you have to both deal, you have to deal with your own city sinking at the same time the sea is rising. So the technique works just by a position in time. So you have the position 1 year here, the next year you have here, or the next day, but there are many days, and from that we can see how it evolves through time. Okay, so that was a bit too opportunistic. To go one back. Okay, for that, I don't want to go into detail, but we use a special scientific software. We have to do that. If not, we cannot get the millimeter precision we require for our scientific studies. And we have employed this already, this kind of work with many other universities and countries, but mostly Thailand, Indonesia, and Malaysia, in a number of projects in the past, I think almost the past 2 decades. So, okay, so I'll move on to the next one. So what's important is, if we use GNSS, is to use the continuous observations. That means stations which are working day in, day out. You can also measure year by year. We call this campaign style, but that works as well. But you can imagine if you have data every day, you can even do a better job. And then what comes out of there, you can see on the right panel, that's we call a position time series. Now, the importance of GPS is, for our studies, is to collect or to have data over as much period as possible. Of course, GPS, the first GNSS system, only became fully operational by the mid-90s. So that's about the time where we can have the first data. Fortunately, we do for a number of stations. This station is another station I show you. What you see there is in the 3 directions. The horizontal direction, it's in the top panel. We call it, or the latitude, so the north-south motion. Then the second panel is east-west direction. And the bottom one, the important one for this project, is the vertical position change. And then if you have all those positions, which are all those black dots you can see there, you can estimate a trend line through that. So that means a trend. So same, the sea level rise gives you a trend, how many millimeter per year. We can do that also with the GPS. And then for the vertical, you can see actually that there also are seasonal variations, which are not a big issue, but you see the signal moving up and down through time. And that's something we're not too much interested in, because it's not really related to, well, it's a yearly similar cycle, but what's more important is the blue line going down, if you see from the west to the east. This is a station which is SPKN, which is near Bangkok at the Khao Phraya River mouth. We've installed back in the end of 2013, and so we have data for that for now already 7 years. One thing, if some of you might notice, that there is a jump there. That's actually a jump in the position. What happened, but not because of an earthquake, but that's something with the monument being hit by a car, we don't know. So, but that's no problem, we can estimate. But it's good to have your station not be interrupted by anything for all the years you measure, because sometimes they might build an office there and you have to move. So we try to keep the same position for a long time. the same stations as much as we can. Okay, this is the technique Mark will tell you about. I don't want to go into too much detail, but what you see here on the right bottom panel is the tide gauge data, and they see the clear increase in sea level rise in the last 100 years. And then like in the last 20 years, we also have the satellites. We can measure this independently, so not using the tide gauge. Of course, if you still have the tide gauge data, you can combine. So you have an extra check to see. And then you can actually see, and that's on the upper panel, that's those last 20 years, which is the last part of the bottom graph. You can see that the satellites also give us the sea level rise. This is the global change. Now you have to know that, but Mark will tell that, he's the expert on that, that you have a global average, but still in different regions of the world, you can have a different number. It can be higher or lower. It has to do with the currents and how the sea works and temperature changes. So that's something you will hear from Mark later. Then we have the INSAR, which again, you get all the details from Dr. Anapau later on. But there you can see that we can measure changes in position in an image, either due to an earthquake, which you see on the left, or to the right, we call it human-induced, and that's because urbanization, a new area is being built, constructed, that mostly has to do also with groundwater has to change, or sometimes has to be pumped to lower it, to put foundations. Of course, you have the weight from the new buildings. They will also add, although that's not the biggest problem. And then when you see red in this one, in this figure, then red means that the sea level, that the land is going down, where the lighter yellow to green to blue colors show that that area is not deforming too much. So this is something we can get from the satellite, and verify. Now the tide gauge, as I mentioned, is less complicated, but still very valuable data. It is basically a paper roll in the old times, with a pen, which is connected to the device measuring the sea level. And as the sea level goes up and down, as it does during the day with the tides, the pen follows and registers it on a piece of paper. That's how it was recorded for a long period of time. Of course, nowadays we can do it electronically, but it comes down to the same, and you just record the sea level for a long time. And we have all those stations around the world, but also Thailand has them. I think the Hydrographical Department operates some. I think Port Authority, there are more, DMR also, there are more agencies who do that for their own purposes. They have to know what's happening to the sea. So if you have this data for a long period of time, it can give you additional valuable data. So that's something else we're gonna mix in in addition to our satellite data. So we go on to the next one. So that already was shown by Femke. So what I only want to show here is that where the red ellipse is, that's where I come in with the GNSS stations to contribute, estimate on the vertical motion in this whole area, the Bangkok or whatever area I would like to study. But of course, in Thailand, we focused in the south of Thailand in the past, in Phuket. Still continue there, but now also we will do more work on Bangkok and see if we can improve on what we already have and expand it with new measurements. So I go on. So I have to talk to you very briefly about plate motion, tectonics. So you have to know a bit about that because it also has something to do with vertical motions. As you know, the Earth crust is built up out of many plates, and those plates, they are floating on the, just to keep it not too complicated, they are floating on the hot fluid interior of the Earth, and they are moving in different directions. In some areas, they move towards each other. In some areas, they move away from each other. So that's where you get, for example, the big oceans when the two continents are being pulled apart. So America, for example, long time ago was connected to Europe and Africa, and then it drifted, so because of the tectonic motion. So that those plates, they can cause many things. Fortunately for Thailand, you are quite far away, But you are also on a tectonic plate. We call it Sunda block or Sunda plate or Sunda land. It all refers to the same. And the plate itself can deform also even up to Bangkok. Although most of the actions, the earthquakes, volcanic eruptions, they happen near the edges where the plates converge. In this case, yeah, and that's, you all know, near Indonesia, Sumatra, you already know, Andaman, many earthquakes happened there in the past. So that's actually important to know. Now, those plates, as I told you, although most of the earthquakes happen on their edges, still they can deform up to many 100 kilometers inland. So it's like if you would push two things together or a piece of paper, you push it, it can move up, and when you then release the force, it will go back down. So that's actually also what happened to Phuket and to some extent to Bangkok during this, we call it a seismic cycle. That's the period in between very big earthquakes when the plate is doing something. And that also creates some vertical motions, which we also have looked into. To illustrate that, I'll see on the next slide. Yeah, so here that's illustrated. And there you can see that all those yellow arrows, they are the motion of those tectonic plates. And you see that they all move in different directions. You have the Australian, the Indian, the Pacific plate. You know the Ring of Fire. Of course, the Ring of Fire is not coming inside Thailand, fortunately, but it's a well-known area where you have all those major earthquakes. And then you have this big seismic cycle, which, if we go one time. Okay, so we have this seismic cycle, as I mentioned. You have before the earthquake, you have during the earthquake, you have after the earthquake. Okay, and those three phases are called interseismic, co-seismic, and post-seismic. Right now, we are, for this big earthquake of 2004, we are in the after earthquake phase. And that's also where we see some vertical motions associated with that. Okay, so that's, we have to go back. My pointer is getting in trouble. Yeah, this one. So what we then see, when we come to the vertical deformation of Thailand over a period of time, we could see actually that before 2004, some areas in Thailand were slightly moving up. That's a good sign if you talk about subsidence. Unfortunately, this was mostly or more in the southern parts of Thailand, up to a few millimeters per year. So you see it's difficult to know, of course, millimeter per year if you're yourself standing there, but the science can measure it. But then we had this big earthquake at the end of 2004. And actually, after everything started to sink, not only Bangkok, but also Phuket. And we even had a rate at the beginning, I think, of like 1 centimeter in the first year, which is quite a lot. So this is just not to you confuse, we call it tectonic subsidence. And it has a cycle of going down, and then when the plates start to deform again, it's going to move up. So it's not a major or a huge problem, for example, for Bangkok, because it's only temporary and it's changing over a period of a couple hundred years. But right now we were in the down phase since 2004. In the island of Phuket, you can see that very clearly on the right bottom. You can see that before the earthquake, so that's about in the middle of the graph, you see that all the black points, although there is some noise and some seasonal variation, they were moving up. And then the earthquake happened, and then everything started to move downwards. But that downward motion now, at the end of 2018-19, was already slowing down. So it's not a big problem for Bangkok, but it is something we have to, just being the detailed scientist, we have to also take along. So now I just want to go to showcase what we have already did in Phuket, where we have combined the GPS or GNSS data with satellite altimetry. We have not used the INSAR there because Phuket Island is a rock island, so we don't have a thick sedimentation layer as we do have in Bangkok. In Bangkok, the sedimentation layer is up to 2 kilometers thick. Phuket, of course, you see it's a lot of rock there, so it's not so sensitive to water extraction, groundwater extraction. It mostly is moving up or down as a result of these tectonics I show you about. We are using there in Phuket 3 stations for GPS and 1 tide gauge station. And we actually have put GPS on one of the tide gauge station, which is measuring the sea. So we can also double check that the tide gauge station itself is not moving vertically up or down in a way we would not know, because it would give a false signal for the sea level rise. So the coast seismic, this is the horizontal area actually, has changed a lot for the whole Southeast Asia, and land moved a lot suddenly. Fortunately, well, the normal people will not, the public would not notice this, but it was up to meters near the earthquake in Indonesia, and Thailand even 25 centimeters. But this coast seismic phase was just during the earthquake. It already passed. So then if we looked to the motions, I don't want to go too much detail here, but a lot changed that before the earthquake, things were moving all the same in Thailand, or similar in the horizontal direction, but in the vertical, similar if it would not be affected by human-induced land subsidence due to, for example, groundwater extraction. But then after the earthquake, many things changed. There's 2 figures there. The one is the absolute, but the other one is the right one is with respect to the tectonic plate. So this shows how the plate itself is deforming and also affects Thailand with that. Fortunately, this is horizontal. This is millimeters. This is not a big issue at all for the general public. But we're monitoring as part of our research, which we're also going to use for the vertical motion. So I'll move on. So right now, as I mentioned, we're still in this post-seismic, and then here you can see this very clear in Phuket. That's the reason also why we choose Phuket in the past. Phuket is located the closest for Thailand to the epicenter of the earthquake in 2004. So any signals we see due to the tectonic, we see the strongest in Phuket Island. At the same time, of course, we learn about the vertical motion, and we can apply this to our understanding, or in a new project, our research for Bangkok itself. So it's a long period of time that the motion goes back to its original motion before the earthquakes. In the horizontal especially, you see that it can last for decades, so 20, 30, 40, 50, 60 years. And also in the vertical, actually, we don't even know in detail. The scientists are still studying, and they need actually data as this over a long period of time to improve their models. And then they can tell us also a bit more mid detail, for example, for Bangkok, how much due to the tectonic Bangkok will still be sinking, although that's never going to be more than 10 centimeters in total. So that's not the big problem for Bangkok if you want to talk about sinking or prevent sinking of Bangkok. Okay. So in Phuket, we added the stations, and a lot of this we have done ourselves. I've done myself personally, because it's a balance trying to find the best station with the best visibility. So you don't want to put it next to an office which is blocking the signal from the satellites. You want to put it on an island, or not an island, on a foundation, something which is strong, which will not be destroyed by the sea or by construction nearby through time. So you set up this control point, and then you put an antenna on top of that, and then you program the receiver, the equipment. We use a solar panel so it can work independently. We use the data, mobile data connection, so it can send the data automatically. So if nothing goes wrong, it will work on for years. It has done so, actually. It has worked for this station for 4 years now. And we've been just to Phuket. We just came back from Phuket to service together with Captain Samart. And you can see the station still there. We actually had a very nice rainbow, so it's not the signals coming to the antenna, but it was a nice moment we could capture. We service, update firmware to ensure that the station can continue to gather data for a long period of time. Because I mentioned you need data over a long period of year of time. You cannot just do a project for 1-2 years and measure, and then after 2 years you know everything. That's not going to happen. So you need, in this case for vertical motion, in the case of Bangkok, we need data from stations which have 5, 10, 15, 20 years if possible. The new stations help, for sure, but to get the big overview, you need to have this for a long term. So it's a long time research you have to carry out. This is the other station we put. We actually put this on top of the tide gauge. As I told you, you can see on the roof, there's an antenna there. And with that, we can monitoring what the tide gauge is doing. While itself, it's measuring, the tide gauge is measuring the sea. But at the same time, we want to know what this whole structure, this building is doing through the years, because we need to know that, otherwise it will give a wrong measurement of the sea level rise. So for that, we equip the station, and after we leave it alone, and we only go visit it once a year, and fortunately, this one is quite new. We have 2 receivers just to make it redundant, so if the one receiver breaks, we can still get the data from the other one. So that's the other data we have looked at. Yeah, apart from that, we also go to the field. We have the other points which we can still measure. This point there in Phuket, it's at the Promthep Cape. It's there already since 1994. So it's a control point, actually used by the Royal Thai Survey Department reference network for Thailand. So it's part of that, and it has been regularly measured for a couple of days each year. And this gives us valuable information. The same applies for points around Bangkok. So they're not measured every day, but they have been measured year by year for a long period of time. So they add, with that, they add to our science valuable information. Of course, the station you have to service there, you have to go there by boat. Due to COVID-19, I was not able to go there myself. That again, I don't have to go myself always, but sometimes because of technical things, it's good I'm there. But then I asked my Thai colleagues to go there, and they did a perfect job. I think this was in March of this year, to go there and retrieve the data and ensure everything was fine. And like this, yeah, we got more data from this station in Phuket. So I told you before that the accuracy or the position we can get with millimeter or sub-millimeter. Actually, what you see here, you don't have to know anything about math, but what you see here is the number of days. So each line represents 1 day of data, and then it shows you north, east, up, which is the 3 directions. You can have your horizontal position in 2 directions, like this. You want to know, and like this, and then in the height. So these are those 3 numbers you see. This is millimeters. And in the bottom, you see for the 2 stations, there's 2 stations there. The one station is PMBC, the other one is the station on the tide gauge. You see those numbers, it says 0. I have to do my best now to read my own, but it's sub-millimeter, 0 point something millimeter. So that means so accurate, a millimeter is very small, we can get, and the height you see is a couple millimeters. That's just for a week. But if we do that for a long period of time, we can really get, very accurately, we can know how something is moving. And of course, other people can check the data. What we have done here is we have the 2 stations in Phuket. And now, just to be sure that the one station is not doing something which is the other is not doing, so it has, because for example, the whole structure of the tide gauge, due to a storm, or it's not well funded, not fixed to the bottom, it might slide, you know. We don't want to have that pollute our scientific data. So we use the one station on the coast, and then the other one on top of the tide gauge, and we just check the position every day in between them, and because they are close together, they should move the same, because Phuket is moving the same at that scale. If not, something is wrong. So at that, we can ensure that the tide gauge platform, as you would also could do with the oil platform, for example, but then it's of course for a commercial reason. This is purely for the science, and then we can actually confirm that since 1 year, I think we have measured it. Before we measured it with just temporary, putting the GPS antenna, but it works better every day, that we confirm that the tide gauge station is stable, at least for the years, the period we have put the GPS on there. So that's something that gives us more grip on the data, and to be sure that we can say that this tide gauge data is validated also with its own vertical motion it has, so we can add that. Because we talked about this before, relative sea level rise. Land going down and the sea going up, and the combination of that, of course, is a bigger effect. So land subsidence in Phuket is not due to human-induced, it's mostly due to tectonic, but smaller and not a big problem. This is actually the result for that study. We did that where we had data from Phuket Island for a total period of almost 25 years of data. So that's a long period, and then you can really study any changes over that period. What we have seen there, of course, is that, as I mentioned to you before, that we don't know how long because we only have GPS data since the 1994, but we think for the last 100, maybe 200 years, Phuket was going up the island, well, not only the island, the area around it in the south of Thailand, around 3-4 millimeter per year. So for the people living on the island, that actually meant that they would see the sea going down. And nowadays in Bangkok, it's a bit different, but that's due to the tectonics. Then after the earthquake, the island started to sink. Fortunately, only for a short time. The total, I think, is there. Up to the end, I think it was around 12 centimeter. If difference with respect if no earthquake would have happened. At the same time, of course, the sea level rise has not stopped. So Phuket, after 2004, saw the sea level rise much quicker. Why? Because the island itself was sinking for a while, just a short while. So nobody in Phuket have to worry about that because you can see it already started to become less. That's just part of this earthquake cycle. Now, Bangkok is a different story because Bangkok was going, well, up or going nowhere vertically, but now we see strong subsidence, which will be shown later. The tectonic is just is a small thing in there. It's a detail, but not something I want to make anybody worry about. But the land subsidence is much bigger, If the land subsidence, I think Dr. Anapa will show, is like 10 to 30 millimeter of 1 to 3 centimeter per year. And we all know that the sea level rise estimates are 3-4 millimeter per year. That's a factor 10. So if Bangkok would not move itself vertically, it would see the sea rise at a rate 3 millimeter per year. And it's per year, but at the same time now, if it's sinking itself by 30 millimeter per year, the effect is much bigger, So anything happening due to sea level rise, climate change, is happening much quicker to a city which is itself suffering from land subsidence. I have good news for Phuket, actually. The coral reef, which we all know is endangered on many places in the world. In Phuket, actually, it benefited from this event because coral reef, especially the shallow water coral reef near the beach, if the island starts to sink, the coral gets more water on top of it and actually protects the coral a bit in these harsh times when there is coral bleaching due to warming of the ocean. So actually this was for the coral in Phuket. For some time it was actually nice that event happened. So it's not always all bad news because we are all suffering, well, the climate change has an impact on the sea, on the animal life, on people as well. Okay, so we're almost ending. Then what we also have looked at is, actually my colleague Mark Naye is the expert on that. We looked at the tide gauge, which you see up there. So it's the measurement of the satellite looking at the sea. And there you see the sea was going up, sea level rise. And then in the bottom one, the one below, you actually see another graph, that's the tide gauge. In the tide gauge, you see something strange. It first looks like it's almost not going up anywhere. And why is that? Because before Phuket Island was moving up at a similar rate as the sea was going up. So for Phuket, it looked like the beach or the water didn't go up or down much. But then after the earthquake, Phuket Island sank a couple centimeters. And then suddenly, because we are sinking, the sea is still rising, the effect becomes bigger. What you see in the second part of the bottom graph, you see a strong signal. We call this the relative sea level rise is much bigger due to the fact that the island itself for a while was going down. due to tectonics, but if it's man-induced like in Bangkok, you see that the effect becomes much bigger. So that's actually what I wanted to make you remember from the study in Phuket. Of course, in Bangkok, we're going to look at the total situation in Bangkok. Okay, so I move on. So this vertical effect that's from the tectonic, it can have a couple centimeters also for the Bangkok area, but then again, that only could be once. I mean, it's going to stop. It's not going to continue. So the tectonic effect is also in Bangkok. We can still see it, but it's small. But if you would build a wall to protect, you could add 10 centimeters extra just to be sure, based on this estimate. Okay. Now it brings us back to, now we go to Bangkok. If at least the computer wants to take me there, yes. So we're going to look at the continuous GPS stations which are available. And then you can see that there's not so many there, but fortunately we have some, and some of them have been operational since more than 20 years. So for this study, we're going to look at those stations more in detail again, what their vertical motion is. Now we would like to have more stations, so I already contacted, and I've been cooperating for a long time with Thai colleagues, so I asked them also, although it's more recent data, there's more coarse or continuous stations now, but they've only been installed in the last 5, 10 years. But I asked them, please give me the overview of all the stations so we can check if we can include them. So if I go to the next slide. Oh, I was one too much, sorry, go one back. Okay, so those are the results for those stations we have ourselves in the Bangkok area. So you have to look to the right panel and to the left panel, the bottom one. The first two graphs on the other side is the horizontal. You don't have to discuss that. But you see that all stations in Bangkok show subsidence, absolute subsidence, up to 5 millimeters per year. This maybe looks less than what you expect of what you heard before, but we should not forget that all those stations, they are located on buildings, or they're located on pillars of a pier, which go 10, 20 meters down into the soil. So what the GPS is measuring is the subsidence below that, because the pillar is going down with the sand below it. However, we know that the top layer, from 0 to 10, 20 meters, the sand layer or the sediment layer can have much higher subsidence rate, because there the effect of water pumping and changing of moisture in the soil has a bigger effect. So you can have much higher rates. But that would be the minimum. If you would not have those upper layers, then you would still have 5 millimeters per year. So that's the same level of the sea level rise. But you'll see that we can even in certain areas of Bangkok have higher numbers. Okay, so I asked my Thai colleagues, please, do you have more stations in Thailand, GPS stations? And yes, they are. The Department of Land, Royal Thai Survey Department, there's many more there, and they all actually already are having contacts with each other. And of course, we are not interested in all of those stations. It's a lot of work, but if we then zoom into the Bangkok area, then it looks actually quite promising, because you see here again, those two red, the green one, and the two yellow stations, that's the one we already were aware. But now it looks like there's still quite more than 10 stations additionally, and we talk about the greater Bangkok region, not just Bangkok city center, but that we expect, or we hope, we have to look at the data, we have to process the data, and see if also those locations are going to give us more information on the vertical motion. That brings me to my final slide, and then it's the conclusion and outlook. So the GPS vertical results, at least over the period of 25 years, they show, as a result of tectonic, that's smaller for the Bangkok area, but still a little bit present, or human-induced long-term land subsidence of 5 millimeters per year. But that is mostly for the soil below 20 meters. So in the upper level, you can still have much more sand compaction due to changing groundwater. So in this study, it's important for us to know, because I say 10, 20-meter pillar, but we don't know exactly. So we have to check for every of the GPS station how deep are, and we hope that the city town planning or other agencies, they can still know, find out how deep those pillars were, so we can know at what depth we are sampling the land subsidence. What is very important for us is that to have a long position time series over a long period of time for multiple locations in and around Bangkok. So that's what we hope. The stations are already there, so we're going to look at the data of the stations which are there now, and hopefully all the data, well, the data, how long they are operate, we'll look at everything for each of those stations, and in the next couple of years, and then we hope to get a better picture using GPS data. And for that, of course, it's important for us to cooperate. And we already, as you've seen, this is also the result on the previous graph. I already put some names from networks and other government agencies. We have the data for other stations, and we will cooperate with them, and we hope we can share the data and analyze together. And actually, that concludes my talk on the GNSS part. So thank all of you, and my colleagues will give you more detail. So we have still some time for questions and answers. Okay, so there's more than the one system we use for the GPS, but we have one of them is installed, I think, near the city center. I think Sanam Luang, you have the old part. We have one of them which is close to the river mouth. It's Samut Prakan. We have one there. So and the other one is, I think, on the top of a building of Chulalongkorn University. So these are the three locations. So it's just a location. You could install it anywhere, but that's for the Bangkok area. And ourselves, many agencies have those stations, but the ones we control ourselves are mainly focused in Bangkok area and then Phuket. Yes. So I mean, the stations we are. The question is, will the system be available for Thailand to use after the end of this project? So what we have done already, those stations we have set up for a long time, a long period of time. All the data is available, and what I have done, because normally if you have a project, you all know that you get funded or money for 5 years. The project ends, and then the equipment is abandoned or it's not serviced anymore, it might break down. We keep the equipment operating for sure. It has been until I retire, because it has become a personal hobby, and we get new funding. And the data also, of course, will be shared. So we hope that the stations will remain, at least the stations we operating ourselves, they will remain active. So thanks for the questions. Okay. Is there any difference of the sea level rise or land sinking between those presented in Bangkok and this year? I think the question refers to that there are many different results might have been presented, or how is it changing? First of all, I want to say something. Any study uses different data or different period of data. So based on that, you can have a different result. However, all the studies, I think, who have been presented, you have the World Bank or many other groups, scientists have looked at us, not cooperating with us, they all come to a similar conclusion. So the sea level rise is really there from a global viewpoint. We can do nothing about that. It's due to the climate change. The land sinking has been seen in the past. It is changing sometimes when different areas of Bangkok are developed and there's a new area. But we have seen, for example, now that in the Samut Sakhon province, I think the Femke showed that already, there seems to be a lot of subsidence going on there. And we know that there's a lot of industry there. The Bangkok city center itself seems to be less severe cases of Bangkok subsidence, but you don't have to forget that the defense comes from the coast. So if the coastal areas are subsiding, the water will just be allowed easier to go. So the change from previous studies, I think we updated it, but they all come to the sound. There is a serious problem or threat from the sea level rise for Bangkok. Bangkok is only 1 to 2 meters above sea level. So you can do the math. If you have 5 millimeter sea level rise, you have 3 centimeter subsidence, that's 3.5. Now that's 10 years, that's already 35 centimeter. Below 30 years, that's 1 meter. So you can know that by 2050, if nothing would happen, and even the new report coming out from IPC today might even show a bigger sea level rise, then you know that Bangkok is gonna be flooded, you know? It's not gonna fall in the sea. So we update the results, we refine them, but I think all the researchers agree also for Bangkok that we have this sea level rise threat.
Thank you very much, Mr. Wim Simons, for this nice and very interesting talk. Okay. It's quite full of the information, really. Right. This is for any listener who would like to ask more questions about to our speakers. You can send the questions to the chat box in the Zoom system by commenting on who you want to ask. And then your questions will be presented at the end of the talk and also at the end of the sessions in this seminar. Before going to the next sessions, let us take a short break. Now we are at 2:25. So let's get back at 2:45, 2:45, and then we will come and meet again. Okay? Thank you very much. See you later. Ladies and gentlemen, welcome back to the International Seminar on Satellite Subsidence and Sea Level Data Assimilation for Mean High Water Line Assessment in the Bangkok area. Our next speaker is Mr. Mark Naye from TU Delft. He will give a talk, and the topic of his presentation is sea level variations in the Gulf of Thailand as measured by altimetry and tide gauges. Please, Mr. Mark Naye.
Good afternoon, everybody. Not sure whether this is technically going to work. Am I visible? Can I be heard? That's actually the first question. So can anybody of you confirm? Okay, I see some thumbs up from my colleague, so that's good. So let's go to the next technical difficulty is setting up my presentation. So I will try to share my screen, see if that is possible. I think it looks like it's possible. So again, the question would be, is everybody seeing my, not sure if this is the, okay. Yes, okay. First try to put it in, okay, I can see it right now. So it is in presentation mode. So as I said, it is good morning. So I would have said good morning. It's good morning here in Delft. Of course, you are already in the afternoon, so good afternoon. For everybody who's listening in the main hall or online at home or wherever you are. My name is Mark Naye, and my contribution to this project, well, we all know what it's about. We're looking at what is the land doing and what is the sea level doing for Bangkok and near Bangkok. My specialty or my expertise is on altimetry, satellite altimetry. So I will tell a little bit about satellite altimetry. Talk of today, for me, sea level variations in the Gulf of Thailand as measured by altimetry and tide gauges. Let's see, I should do it, I think something like this. Well, let's start off with the technique which we call satellite altimetry. It's not for nothing that it's called satellite altimetry. We have a satellite encircling the Earth. And what is this satellite doing? It's observing the oceans. And basically, if we look at the left animation on this sheet, we see that the satellite is sending a radar pulse towards the sea level, where it's reflected at sea level, and then it's sent back to the satellite. It's received back to the satellite, and actually the time that it needs to get to the satellite, the shape of the wave that is the radar wave that is received on board of the satellite gives an idea of some of the parameters of this sea, and that is explained. So now we see this sending. This is the returned pulse. The timing is actually the sea surface height. We see the gradient of the leading edge. This gives an idea of the significant wave height, and the total power received back is a measure for wind speed. On the right animation, you see these waveforms being measured every second. Actually, if you take a look at the right animation, but there the left image, you see kind of 1 per second measurements. This actually every 7 kilometers along the track, we get an idea of the sea level. Now with a newer technique, this altimetry technique, let's say a conventional technique that already started somewhere in the 80s. Nowadays, this measurement evolved, and we have what we call SAR altimetry, and we can get much higher resolution along track. So that's what we see on the right-hand side of the right animation. Now, having this measurement, and we see the satellite here again, and what it measures is what we call range. This is what is the satellite height. Well, the satellite height, it's not the satellite height. Normally, the satellite height we express with respect to a certain ellipsoid. Not sure whether my own arrow is visible. In principle, the measurement itself, or getting to what we call sea level, is not that complicated. It gets complicated in the part where we say, okay, we need some corrections. And the pulse travels through the atmosphere, it goes to the sea level, it's reflected there, it travels back through the atmosphere. So there are things in the atmosphere that will delay the pulse. And if you know exactly the speed with which the pulse travels, yeah, and you time it, how long does it take to go from satellite to sea surface and back, then you have actually 2 times the distance if you know the velocity. But this velocity is in principle the speed of light, but of course it is delayed due to electrons and also water vapor and that sort of thing. So we need a couple of corrections to this what we call range measurement. So basically what is measured is the range between the satellite and the sea surface. Let's call that that is the H in this picture. We call it altimetric distance. Now, you only can get to what we call sea level if you know where this satellite is with respect to a certain reference. We, for that, take the reference ellipsoid. So that is the lower line, curved line in this plot here. So if we know this r, and the small r, the satellite height with respect to its reference ellipsoid, and we would subtract, so we have the r, the orbital height, we subtract the measured distance between satellite and sea surface, then we get actually the sea level or the sea surface with respect to that reference ellipsoid. Now this sea surface or sea level consists of a large part which is regulated by the Earth's gravity. So we call that the geoid. So whenever there's no currents, no variations due to atmosphere, for instance, then the sea level will sort of point to the local gravity. And we call that marine geoid. So that is the large N, the capital N in this equation. And we have a smaller portion which is indicated here by S, and we call that dynamic topography. For oceanography and ocean circulation, you would be interested in something called dynamic topography. Of course, if you're interested in what is the sea level on a whole doing, then you want to have the absolute sea level total. Now, this is something that I use in my lectures when I plot all of these measurements the satellite is doing. The thing I ask when I just show this picture is, what are you seeing? So that's what I ask my students, what are you seeing? And of course, most of the time they will say, well, what we see is bottom topography. We see sea mountains, we see lower parts, higher parts, but basically this is not bottom topography which is plotted here. It's just the sea level measurements. But as the part due to the gravity is the larger part of the signal, when you take all the signals together, all your data and average, you end up with a picture like this. So we call that the mean sea surface. What can you do if you measure something? You can take a look at the mean. And how does it work? Why is it looks like that it is bottom topography? Well, it's like if you have your water profile, it will point, or actually the perpendicular to the local gravity. And so, as an example, we have an excess of mass here within the bottom topography, but you can also have a sea mountain, which is also an extra mass, can consider to be an extra mass. Then also your sea level will exhibit this bump in the sea level. It is what we call a service of an equipotential service. So you find along this bumped line the same gravity, and you see that it is indeed curved because it points towards this local mass. It's not the direct attraction of the mass. Otherwise, of course, there you would have a sort of a valley in the sea level. That is not what we are seeing. It's just the water rearranging itself to point towards the local mass axis. Now, that's one way of looking at the data. But if you take the average, take the mean, then you basically have the geoid or the gravity contribution. If you take out this gravity or this geoid contribution by not looking at the mean, but looking at the variability, so what is changing over time, and that kind of assuming that the geoid itself is not directly changing, or at least not changing much, yeah, we call that variability. And then, of course, you get a totally different picture when you take all these altimeter measurements and variability, standard deviation. That is, of course, the individual measurements, and then the mean subtracted, and then RMS together. You get a kind of image where you get enhancements where the variability or the kinetic energy in your sea level is highest, and that's why you see these enhancements so connected with what we call the western boundary currents. So Kuroshio here, Bolas here, Brazil Malvinas, and of course we have the Gulf Stream over here at North America. So what can we do more with the data? So you can look at the mean, you can look at the variability. You can also see if there's any secular change over time. So looking at trends. As we have our satellites encircling the Earth and also repeating its orbit, we can actually every orbit, and it depends on which satellite, but it can be a 10-day repeat or a 35-day repeat. But then you can make. It takes, for instance, for TOPEX Poseidon JSON 10 days to get to the same sampling of your sea level. And what you can do is just take an average for that 10 days and then follow that in time. So take the average of the next 10 days and the next 10 days and the next 10 days. And then you end up with a plot that we have here on this slide on the top right. And basically what we started to see with the advent of altimetry, of course, we already also saw that in tide gauge readings, is that we have a rising sea level. Now, on average, at the moment, it is around 3 millimeters per year. The bottom right figure is actually also giving this number or this altimetry solution. That it's the red line, and we just started somewhere in the 90s with this with altimetry, or at least with the, let's say, serious precise altimetry measurements. Before that, we used tide gauges, and you see there's also more spread in there. The number we got from tide gauges is like 2 millimeters per year. But if you look at the sampling, tide gauges are, of course, not homogeneously distributed over the Earth. They are so close to the land, whereas altimeter is homogeneously distributed over the Earth. So I would say with just tide gauges, you miss a bit of the total picture, and with altimetry, you get the total picture. Now, we're doing, let's say, this altimeter processing and looking at altimeter data, analyzing it globally, but also for certain areas. We are actually involved, and I think my colleague extensively talked about that. We are involved in several projects that are considering the waters around Thailand. Now, you talk Yeah, so some pictures here. Most common, you have a float operated pipe or a stirring well. That is the old-fashioned way of measuring the tide gauge. Nowadays, you have acoustic sounding tubes or even microwave radar. And what I said, they move vertically with the wind, and you can have something like tectonic uplift, subsidence in the land, and that, of course, is also in your tide gauge reading. Now, you can tie, and that is basically what we also try to do, and we have for certain tide gauges tied the GPS, let's say the absolute land motion in the vertical to the altimeter. The two bottom pictures. This is well, you might have recognized my colleague Wim Simons. We have it's not our tide gauge, but it's a tide gauge in Bangkok, and we operate or we put there a GPS receiver and GPS antenna. Okay, so tide gauges and sea level altimetry. Let's see where. I do have to refer to one of these earlier projects we have done. I think the Geo2TechD that was especially for Thailand and the surrounding waters of Thailand. We did extensive research with SAR, with INSAR, and with GPS, and with altimetry and tide gauges. And from altimetry, you get something called regional sea level dynamics. What we did for this particular area, so it's a little bit bigger area, we take the altimeter measurements, we make something we call sea level anomaly. So there's a mean sea surface model we subtract from all the individual measurements, and we combine measurements for a week, and then we follow that in time, and you can get to a animation of what the sea level is doing. So we'll start the animation. What you see in this animation is, well, predominantly you see things just popping up and going away. So getting higher, getting lower. So that is basically the seasonal cycle. What you see there. Some things are transient, so you do see things moving from from the east to the west. And you see these highs in the Gulf of Thailand. This is just ocean dynamics, so this is not sea level rise or something like that. It's our seasonal cycle. Highs in the Gulf of Thailand around January, March. And there's a clear annual cycle. Well, you can get an idea of what the annual cycle is by fitting a model to the data, which includes a bias, an annual cycle, and also a semi-annual cycle. And that's also what we have done. So I'll show the result of that. Okay, so this refers actually to a paper that came out during that project. So we're now 2010, 2011. You see here the database actually. So what is the altimeter data we have? Those are the tracks and the grays and the blues here, and we also have the tide stations. And on these triangles, those are our GPS stations. I think an important outcome of this project, also the idea started to arise during this project, to combine all these measurements, and we have in our table for some of these tide gauge stations, we have for this time period 93 to 2009, and this is all millimeters per year. So these are trends. What came out of altimetry, and also this is the first column, and then we have the tide gauge. So that's the fourth column, tide gauge here. And we combined the information from the altimetry with the tide gauge. And as I said, the altimetry gives the absolute sea level, whereas the tide gauge gives sea level with respect to the land. So if you subtract the two and you read for tide gauge, actually sea level minus vertical land motion, then you have sea level minus sea level plus vertical land motion. So this combination, altimetry minus tide gauge, gives you the vertical land motion. And then we can also compare that with the vertical land motion we get from the GPS. And that is in the file. So the GPS is in the final column. And as it appeared, it's not, let's say, working for each of these stations, but most of them, yes, and also within the error margin. So this was a very nice result. Basically, this also means that the moment, and so now we have all three of the data for certain locations, the GPS, the tide gauge, and the altimetry. And if you can sort of prove that it works, so you have one as a kind of a validation for the combination of the other two, then you can start going to areas where you are just missing one of these items, one of these informations. So this was an important outcome of this project. I think another interesting outcome of this project, and basically is the start of our this new project, is when you have the evidence of land sinking and water rising, you can start combining that with GIS models and do some forecast for let's say the next 50 years. So you can then generate scenarios for any given time and location. And it was the very start. It was not worked out further, but what we see here is what is said in the text here. So this is a sea flooded area in Bangkok, Samut, January 2016. So that was for then 2010, a forecast for 50 years. We have the GIS-based model, and we combine effects of sea level rise, plate downlift, and land subsidence, and all the areas which are here green coded have let's say a mild submerged of the land, so it's like 20 centimeters, but we go to red where it is let's say a meter and more. This could help you with, let's say, defining areas where you would like to either, when there are already dikes, to enhance or higher the dikes, or let's say, choose locations where you add new dikes. So I think that was also an important output of that project. Recent results just shows we have taken more data. Here we have what we call the sea level change, millimeters per year. And when we are, and this is up to 2019, I think. What we see in the Gulf of Thailand, yes, we see this combination of green and yellow, I think it's a bit orange, just underneath this spot, which indicates Bangkok. So this is what we can do, or what we do with the data. So as I said, we put a model through that, which we try to extract the bias itself. You just saw in the previous slide the bias, but we can also look at the annual cycle and the semi-annual cycle. And we have here in this column the amplitude, that's on the left, and we have on the right the phase, and on the top we have the annual, and on the bottom the semi-annual. So we see a very strong annual cycle in the Gulf of Thailand. We see no semi-annual cycle in the Gulf of Thailand, but there is the semi-annual cycle in the on the other side of Thailand. And if you want to see where this maximum, for instance, is, this annual maximum in the Gulf of Thailand, you go to the phase, and phase is around, what is it? Oh, we have to subtract 90. Well, it says degrees. You have 360 degrees for the phase, and you have 365 days in a year. So a degree is approximately a day. So you can pinpoint this maximum at around what I just said before. So January, February of the year. Probably I don't have to tell too much about this this picture. I'm pretty sure that I did not have the time to look at my colleague's presentation, but I can imagine that he has shown this picture. The nice thing again is here the combination of altimetry, tide gauge, and GPS. And for Phuket Island, we have a nice altimeter record. So that's the top picture, the top figure. We have the tide gauge record, and we have the GPS or the DNSS record. And the nice thing I think of this, and you actually already see that we have the absolute sea level with altimetry, and it is quite a steady rise. It is like 3.9 millimeters per year for Phuket. If you do that with the tide gauges, it's not an absolute measurement, it's a relative measurement. So anything that the land is doing is included in the tide gauge. That is what you see, of course, at the end of 2004, the very large earthquake we had back then. And then the land started to, it was going down, and it was also relaxing after a while. This is also visible in the tide gauge. So it's very nice that if you subtract this and the middle plot from the top plot, you arrive at something that is quite close to the bottom plot. And I think that is also a very nice result. And there's a link to the paper that describes this a little bit more. We're doing the same thing for our tide gauge or tide gauges near Bangkok. So here we have the latest result for the Bangkok sea level. Altimetry on top, and we have the tide gauge at the bottom. Now here we also see something happening, around the early 2004. So that is not due to the earthquake. This was a problem with the tide gauge itself. I think back then it was there was a boat that hit the tide gauge, or at least where the tide gauge was located. And there was a new tide gauge installed, and you see that after the March 2004. But that has a different different character, the different signature. So there is also something with the land that we at the moment do not really let's say model or do not understand. So of course, if the tide gauge is attached to the land, but if it can be attached to what we call the bedrock, or it can also be attached to some layer of then you can have compaction, you can have you have sediment layers, and so that could be something that is included as well. So that this really needs a bit more attention, and that is also, of course, why we have our current project. So some preliminary conclusions for Southeast Asia sea levels. The absolute sea level in Southeast Asia is rising due to climate change, as suggested from altimetry. I think that this will also be confirmed by the IPCC report that will come out today. For Thailand and Malaysia, it varies between 3 and 5 millimeters per year. Let's not make it worse. Whether this is a threat depends on what the vertical land is doing. Of course, this can be answered by GPS, tide gauges, or interferometric INSAR. Having all these techniques at the same time, same place, results can be used to calibrate any of the measurement systems, what I actually just displayed, talked about. For instance, the combination of altimeter, absolute sea level, minus the GPS vertical land motion should give the tide gauge relative sea level, and so forth and so forth. Had a combination. If you subtract tide gauge from the altimeter, you get your vertical land motion. And you can also combine, of course, the GPS with the tide gauge, and that would give you the altimeter reading. As long as we are certain that there are no other, let's say, things are going on, like sediment compaction. All these space geodetic techniques can be applied everywhere on the globe, are almost always available. They are indispensable for ellipsoid-based vertical datum transformation. Sorry. Now, the megathrust earthquakes, we see that in Phuket. Of course, Bangkok is much further away from where most of the earthquakes takes place in Indonesia. So we have a little bit less to worry about these things in Bangkok. But there's still some post-seismic motion, and they contribute to falling land, and that will increase the relative sea level, as will groundwater extraction. So this is really something to be investigated further. I'm not sure if there's any time left, but I also want to make some kind of an advertisement here, some PR for what we call the Radar Altimeter Data System, RADS. This is actually a system, a database, which contains, I would say, all altimeter data up to date, at least the 1 Hertz data, is maintained and organized by UMATSAT, NOAA, and the TU Delft. And if you go to the web portal of RADS, you can read stuff about it, and you can also do a local install of RADS, and then you have to go to the GitHub for the RADS system to get the software to have it installed. This is the data that is at the moment in our database. So it goes back to geosets. These are the halfway, the 80s. ERS 1, Topex, and we have our JSONs. And nowadays we have JSON 3, Sorel, Cryset 2, and Sentinel 3A and Sentinel 3B. So that's not in this table, but we also have Sentinel 3B. And we start to get Sentinel 6, that is the very latest altimeter satellite. And I think I will stop here. This is what I wanted to talk about. But if time permits, I can take a few questions.
Thank you very much, Mr. Mark Dyer, for your nice presentations. Right, next, our speaker will be Ms. Jenny Sunthorn-Rangson. She will give a presentation on the topic of preliminary hydrological data analysis for the Bangkok area. Please, Ms. Jenny.
Can everyone hear me okay? I hope so. Okay, thanks, Lim. My name is Jenny Sunthorn-Rangson. I am a PhD candidate at TU Delft, and thank you for the introduction. Like the introduction said, I will be discussing preliminary hydrological data analysis for the Bangkok area. So I know that FEMCA has introduced the project to also include a sea level analysis, but since the project just kicked off, I'll be focusing primarily on the first stage, which involves groundwater and subsidence. So earlier studies have shown a strong correlation between substantial pumping in the Bangkok area as well as significant subsidence that occurs throughout the city. And so in response to those studies, the government introduced measures to start regulating pumping. And they've started that since the early 2000s. And now we see that groundwater has recovered mainly to where they were before the pumping. However, what we see today is that subsidence continues to occur at lower rates. And so our goal right now is to investigate the historical and the current relationship between groundwater and subsidence to ultimately be able to simulate subsidence based on various pumping scenarios for the future. And we're also interested in doing this at various locations throughout the city. And so I would like to introduce a method that Femke had mentioned called time series analysis. And this particular method is really powerful in that it's able to allow you to see the individual effects on a time series that you're interested in. So for example, for groundwater, you can look at the individual effects of, say, pumping and groundwater diversions or climate change, such as changes in precipitation and evapotranspiration, and seeing what those effects are on groundwater levels and seeing which ones are the important ones. And so I would like to demonstrate by showing you an example. And so this first upper graph here is a time series of measured head. And so you see the daily variations increasing and decreasing. And this particular well is located near the ocean. And so some of the inputs that they are interested in is the sea level. And so here the sea level mimics groundwater levels quite well with the daily variations. In this green graph here, you have a time series of rain. And then in this bottom graph here, you have a time series of the discharge or the pumping. And so based on these three inputs, sea level, rain, and discharge, you can simulate groundwater levels to coincide pretty accurately with the time series of groundwater levels that you observe. And so here simulation is shown in blue, whereas observed is shown as the black dots. And so you see that it's mimicking that daily fluctuation quite well. What's also neat about this technique is that you can see which of these inputs have the most significant contribution to our simulation in head. And so as you might have guessed earlier, seeing that daily variation in sea level might allow you to deduce that, that was the input that was going to have the most influence on head. And so we would like to be able to utilize this technique on our project as well. And so with time series analysis, we want to answer the following questions. How much is pumping actually contributing to the groundwater head variations that we see? And then subsequently, how much is pumping contributing to the subsidence variation in Bangkok? And so with this time series analysis for this project, we would like to first start off with developing time series analysis models for groundwater levels. And these are the stresses or the drivers, the inputs that I mentioned earlier that we would like to input into our model. So that would be groundwater pumping, meteorological data, and that would be important in terms of recharge into the aquifer. And then lastly, the river stage, which is mainly important for the wells close to the Chao Phraya River. And then once we have these, we would then develop time series models to simulate subsidence. And now we would have the inputs as the stresses that I mentioned earlier, but now also groundwater levels. And so first off, I just want to cover briefly what we have in terms of data that's going into our model. So here we have the location of well nests located throughout the city, courtesy of the Department of Groundwater Resources. And so here you can see that our well nests are located throughout the city, as well as in Samut Prakan, east to Minburi. So it's located quite well, distributed quite spatially well. Each of these well nests have wells that are drilled into different aquifers. And I'll show you an example of that later. So some well nests will have some wells that are drilled into the PD aquifer that Femke showed, or the NL aquifer. Next, not only do we have groundwater data, we also have subsidence data. And so here, shown for the southeastern region of the Bangkok area, I show that the INSAR data that we have from Sentinel-1. And so this is subsidence levels from about 2016 to 2021. And this is relative. And so you could see that relatively, most of this region is not subsiding much anymore, but most of that subsiding areas are concentrated in the southern regions, in the Samut Prakan region, as well as the eastern regions shown in red. Not only do we have INSAR data, but we also have leveling benchmarks data courtesy of multiple departments from the government. And so for our Bangkok groundwater, I would like to show you the groundwater levels for LC SPK 007 here, demonstrated by that blue arrow. And so for this well nest, I am showing head groundwater levels for two of the wells. One well, shown in red, is located in the PD aquifer, and this is the shallower well. And then the other well, NB, is the deeper well. So here you could see that in the mid-1990s, we see a dramatic decrease in head. And then from about 2000 on, we've been seeing it gradually increase and steadying out. And so what is causing this? What is causing this trend? And so one of the things that we think is causing this trend or having a significant influence on it is groundwater pumping. And so this bottom graph here is showing the estimated total pumping, shown as this top line here. And it's increasing from the 1950s onwards and maxing out in the mid-1990s. And so that's correlating quite well to this drop in head in groundwater levels that we see in the mid-1990s as well. And so that's one of the main correlations that we see just visually already. Now, we want to include all of this into a time series analysis model that I mentioned earlier. So we're inputting things such as meteorological data, groundwater pumping, a river stage if we have it, and we want to first simulate groundwater, and then we want to simulate subsidence. And so this is just an initial attempt to simulate subsidence that we have. And we want to do this for the historical period when we have a lot of pumping, and then for current periods when the government has introduced measures and there's not a lot of pumping going on. And so this is our first look at simulating subsidence for this well NB30, and our observations from benchmark leveling campaigns are shown in black. And so you see that subsidence back in that region, back in that period, was around 5 millimeters per year, which coincides with what Wim talked about earlier. And so our simulation, based on the inputs that we gave, are shown in blue. And so that's fitting relatively quite well with an R squared of about 80-ish%. Now, we also want to look at simulating subsidence in the current period when there's not a lot of pumping. And so what we see here is that observations, again, are shown in black, and then our simulated is shown in blue. And here we have a lot of noise. So this subsidence observation is from INSAR, and it's showing a lot of noise. And so our simulation the fit is not quite good, but we see that it is capturing that slight negative trend that we still see to this day. So the lower subsiding rates that we see. And so some initial takeaways from starting off this project is that we do see correlation between groundwater pumping and subsidence. This is especially true during the historical periods when we see substantial pumping. However, for current periods, this is harder to interpret, with less pumping going on. And so factors such as meteorological data influencing recharge may be more important during this time now. And the strength of the correlation, how strong that correlation is also location dependent as well. And a lot of people are also interested in the effect of loading from buildings. And so since we don't have a time series of loading from buildings, this effect is not quite known yet. And so moving forward, we would like to clean up that subsidence time series in the current period and to be able to simulate that much more accurately. And so thank you for your time and your attention.
Thank you very much, Ms. Jenny สุนทรรังสรรค์ขอบคุณมากนะครับคุณเจนนี่ครับ Right, next will be our last lecture on this seminar. Our speaker is Dr. Anupau Opad. He will be given the presentation on the topic of land subsidence study using INSA techniques. Please, Dr. Anupal. เรียนเชิญครับ
Good afternoon, everyone. So I don't know if you can see my slide presentation. Is that okay, right? All right. Today, I'm gonna give the topic not just only land subsidence in Bangkok, but I think the thing that I would like to say today is that something really important for my country. Since we have a long time series of the data, the satellite data, and then now it's become the SAR golden age in Thailand. What's about the SAR golden age in Thailand? It means that SAR-based remote sensing for engineering adventures and the geophysical parameter estimation will become much more really important. So let's introduce myself. My name is ผู้ช่วยศาสตราจารย์ Dr. อนุเผ่าแพทย์ from Department of Civil Engineering, Faculty of Engineering, เกษตรศาสตร์ University. Well, SAR golden is, this is the word to express the currents and future SAR stream in the world during 2012. After the launch of Sentinel satellites, and then we would really have, the free of charge of the SAR data, which in the past really expensive. And the basic discipline behind this is the ability of acquiring the data day and night and under all weather conditions. And, ease of mathematical equation, ease of multivariable equation of the microwave in the interferometric and polarimetric term. So this is, let's see what we are going to do. More than 10 years that I spent lots of time, working with INSA. This is like Steve Jobs, said that to love what you do, right? This is, really the real love that I, work with the INSA after my actually from my PhD. And then until now, I still, keep on going like wind. And you can see the past results of the INSA for Bangkok subsidence from 2005 until 2012, which is, at the time I tried to get the data. I used the RadarSat-1, try to, continue doing the time series data. But after 2012, it's unlucky that we lost the data, the RadarSat-1 satellite, which is the Canadian based satellite. So after that, we have no time series data from satellite. At the time of I made the publications about the using site interferometry in Bangkok area. And then I try to validate the data with leveling survey technique, which is, really important that we found that, 80% of INSA and agree with the leveling data. And then if you ask me for now, since 2018, as Femke already mentions about the continuing data, we don't have, leveling data anymore since 2018. So for now, I would inform you that only SAR data that we still have available for the Bangkok area. This is the result from the last time, Geotech, the Geotech 2 project, which is the conclusions of the project that we, from my professor, Dr. Iti, the sea level rise, and then land subsidence, and then the tectonic drawdown, and then we simulate. This is, I think, we already mentioned about. We simulate the flooding area the south of Chao Phraya River. And then after I quit the job at GISTA and become the lecturer at the university, I and Department of Groundwater Resources, we are trying to establish the time series data for RADARSAT-2 again. So remember, we don't have RADARSAT-1 anymore, right? But we're trying to do with the RADARSAT-2. Why RADARSAT-2? At the time, because we have like the RADARSAT-2 data in our archive. So we try to make the planning and then establish the time series data. But even we know at the time that we have the Sentinel-1 data, but our knowledge, our model to work on the Sentinel-1 still really difficult for the people to do. But anyway, we got the result at the time. The subsidence still around plus 35 millimeter per year, and then minus 34.2 millimeter per year. So this is actually about the seasonal variations sometimes. Yeah. And then now we are lucky that we have the cooperation project with UDEL, and then also Dr. Andy Cooper from University of Leeds, which is we have a long time collaboration with the INSA, and I really gained a lot of knowledge from him. With the power of the processing at the University of Leeds, Dr. Andy and his colleagues produced the INSA map from Sentinel-1 satellites. This is back to the years of 2014, if I remember. Yeah, and then until now, and then, but actually, the time series data still, they keep going on collecting the data on our area. So I'm checking, and it's still fine for me. And then also I trying to to process to do the time series data by our own, and then we also get the data from 2018 until 2012, and this is the initial result, as well as the result from University of Leeds. It is still the initial result, so we have to work more on that. And then for now, if take a look back to the data gap year, I can conclude here that I think only 2013 and 2014 that we still have the data gap. But from 2014, I think we can have the satellite data to process with no problem anymore. Well, we may try to use some satellite that they have the data archive at the time, maybe TerraSat or some other satellite. And with the Sentinel-1 satellite, we really, today we really lucky that we have the free of charge satellite to use for the application, like to study the land subsidence in our area, because we couldn't find any other scientific measurement to measure the very large coverage area, like using the satellite. And then you can check here that, we have the Sentinel-1 and V, and if it's still, kept going, capturing the data in Bangkok area, and then we still have like time series data and monitoring for the long term. But anyway, it is something that you have to take into account that this is not our satellite, right? This is not a Thailand satellite, so it's sometimes you have to think about it. And why monitoring using SAR? So we must understand the technique of scientific measurement. If applied in engineering practice, I'll bring down from scientific practice to engineering practice, and I'll point out to show you that how to do that. What it must be viewed from an engineering perspective, very important and sometimes very difficult to both sides understand each other. Then the space-based radar is really the advantage of this technique is the broad coverage and relative low cost, but even really expensive in the past. And for now, when we have the Sentinel-1 data available, everything can get down, like lower cost and easy to deploy and use for carrying out the operation asset and see through the cloud and fog. As you know that in Thailand, they're really tropical country, and then you can see the cloud cover all the time. So the SAR satellite can come to solve the problem. And then this is the very easy concept, right? The radar concept is just like the echo and the signal from the satellite sensor, is penetrate through the cloud and then hit the object in the earth, and then the signal go back to the receiver at the satellite sensor, and then you can easily see the very easy application like flooding application or something, because when the radar signal penetrate to the area that have the water, the signal cannot return to the satellite, and then it's become we call dark color in the SAR image. And then another thing that we have to consider about is that we have the data in both this ascending and descending orbit. So why is so important? It's important because sometimes you want to see the Earth, and then the look of the radar in both sides is different. So sometimes you have to think about, because the radar capture the signal not in the nadir direction, but they have to have like what we call slant range. They have to have the look angle, and then it's gonna capture the world. It's not the same as the optical sensor. And then after if we use two images of the radar, the first image is you capture the image before like the earthquake or some event, some situation to make the earth move occur, and then you get the other image after that event, and then we try to process to see the phase difference, and this is called differential in SAR using just only two images. But in Bangkok area, you cannot do that because you have to, you need the time series of the data. Only two images not enough for study the time series data and slow movement. Just only the big earthquake that we can use the differential in SAR and then get the good result. And then it's pretty concept. You in the interface of radar, it contains many kind of phase error like topographic, ionosphere, them or baseline and noise error, and then they have deformation phase. So the model is we are trying to remove all other phase and then leave just only deformation phase, and then we get the result. However, if we like the information signal doesn't seem too strong enough, and then we can see nothing. If someone wants to try differential INSA, they can use like the on demand. They can put the parameter, put the days, and then this website from Alaska Satellite Facility, and then they can use the what we call the small baseline criteria to choose the INSA, the image pair for you to make the interferometry, and then you will wait just only 3 hours, and then you get the result of the INSA data. Very easy, just only press 2 times, 3 times, and then you get the result. And this is what I have done with Dr. Paisan and Dr. Pasakon just last week. That we just try to do something, based on the earthquake, the Laos earthquake, 6.4 earthquake in Laos back to 22 November 2019, and then we just see something, But that's not enough because we need the time series of the data. Using the differential only to time period, not enough. So for many years, I have been trying to expand my understanding of the technique in engineering. How to use the scientific data to in engineering field. So I think that we have to, keep going on time series data, but it's sometimes very difficult. As I already showed you here, is that if we have done differential INSA like landslides or earthquake applications, what we have done just only in the beginning step, that's nothing. So we have to work on that using the time series. With the technique, many kinds of technique available actually for the time series data, like persistent scatterers, short baseline or small baseline, or combine together. And we are lucky that we have working with Andy for a long time, and then we have the open source and free of charge software, and we can use it to process the data, and we can modify some parameter, and then whatever you want to do is about the processing. So it means that it's really different from using the website that belongs to other agency, and then you can do nothing, just only press, and then you get the result, and then you cannot even translate the result. This is the example, when we get the data from, this is back to the year 2012, when the earthquake occurred in Namma, Myanmar. And then we got the data to one pair of the data before and after. And then we get the earthquake results like post-seismic or something. And then this is not enough. We have to work more on. We are trying to, at the time, create the model and trying to see after that, establish the time series, see the post-seismic, what happening at the time in that area, and then calculate the Coulomb stretchings. Many more things that we have to work, as I already mentioned. This is, just not just only, have the data and then have the model and then trying to process and then get the result. And after that, you know nothing about, no. You still have a lot more to work on. So my question is that what more for Thailand taking benefit from SAR and INSA? As I trying to explain a lot about the benefits of SAR data in Thailand, there's a lot more application that you can use for, and almost every day, and it's a lot of things that you can do with the data, not just only having like using the optical and see the beautiful picture of the Earth when you're watching in the Google Earth, but inside the radar signal, if you zoom in for the result of my past research, you can see some kind of what we call observation point. We have a lot of observation point, not only like 1,000 and 2,000 like leveling data, but we have a lot more, like 200,000, more than 200,000. And if you zoom into that, you're gonna see the points on top of the building or infrastructure. And then if we can clarify that, and then we can separate the observation point, which one is on the this building, which one is on that building, and then we can separate the subsidence rate of the from the observation point. And we can take benefit from that. We can study, we can use this for structural monitoring in the future, but it's just in the beginning, I'm just trying to learn about that. And then many paper publishes, and we can, using my link to Google to see what they are doing, And even my past experience about using the radar, is radar Sat-1, using for monitoring the coastal zone over the eastern inner Gulf of Thailand, and then we still have the good results on that. And then even outside our country, visit Myanmar, Yangpung, we still we are able to use the radar data and then trying to process and see what happening in that area. And then I'll take you to see what Netherlands have done so far, using taking the benefit from SAR data. The use is for subsidence monitoring, and then they kind of establish the service, and then using the satellite. I think it's many source of satellite, and then look at the other area, like inside or the embankment dam in Norway. We can monitor the big structure. In China, they also have the time series inside for 3 short dam monitoring. And then this is the monitoring of dam in Iraq. And then also another application that we can do using inside, like the solution for oil and gas and mining, in many countries, they use the inside in many kind of applications just like this. And then one of my research is, to detect the offshore platform in Malaysia, in the cooperation with the University Technology of Petronas. And at the time, we used the Terasa X data to monitor the offshore platform. This work. And I think that, in our country, we can adopt this technology and then trying to apply to many applications. This is what we can do. Also, the mine monitoring, we can use the satellite also. And this is the overall, like if you want to use the satellite for surface asset monitoring, and then you have many kinds of measurement, and satellite or SAR satellite is one of the measurement. You may have some other measurement work together. This is okay. So here we come to the SAR golden age in Thailand. Survey engineering has entered the geodynamic era with the development of Gnns core station and the INSA technique. So from the subsidence, many deformations can be measured using the same different technique. So we have to be more concerned about it. And the study of infrastructure health monitoring require more paradigm shift to analyze this. So it's still difficult, I know that, but we have to start now. And then, as I already mentioned, we have to use, INSA with other geodetic technique like Gnns and maybe corner reflector, which is really important to reflect the radar signal, and then you can see the bright in the image. In some country, you can see the satellite survey units just like this. So we may be applied in our country to monitor the infrastructure. And then the top 5 challenge in monitoring with INSA. The first one is require regular monitoring. And the second one is the high cost of the data, but now not really high. But it depends on if you choose the really high resolution, like if you want to the data from Terasa X, which is, really have high resolution, and then you have to pay more. And then the number 3, if you want to monitor like in the area really far away and there's not many building there, but you still, can capture the image in that area with a good signal using the corner reflector. Then level of detail is coverage. Yes, the coverage area from inside is very good. But this is a trade-off between the resolution and the coverage. If you have the high coverage, and then your resolution will be, lower. And then the lack of inside expertise. This is important in our country. I try, to teach our students in Gnns University, and then we are still in the beginning of the thing. But anyway, this is important. And let's take a look back the olden time of science in Thailand. This is a 10 year that really have the adventure. Look back to the 2008 when I worked at the Alaska Satellite Facility. I met Fran Meir, and then many things happened at the time. This is just the really beginning. And then I got the second opportunity to work with him, and many other nice people at Chulalongkorn University, also with my professor, Dr. Iti Siri Satayawong, and Professor Ramon Hansen from TU Delft at the time. And then after, later on, Dr. Andy come, and then we work closely with Dr. Andy up to now. and then really have a good memory on that. Also, Dr. Chalamchon as well in that project. We really have good time. And then I think this is all my presentation today. Thank you very much.
Thank you very much, Dr. Anupao. ขอบคุณมากครับ Dr. Now we come to the final part of the sessions, which is question and answer sessions. We have some questions from the listeners. Okay. Please bring the questions to the screen. Questions to our speaker, Mr. Wim Simon. Okay, please, Mr. Wim. Please step up on the stage. I think it's better. Thank you.
I should put my glasses so I can read. I don't see the question. Maybe somebody can read out the question. I see. Oh yeah, just give. Can still see, but that's too small. Okay, so the question as asked, I think it's not maybe only I'm the only expert to answer that, but I'll do my best. So, from all the data available, President, what step Thailand sites should be taken to slow down land subsidence in the areas investigated? Is there any more effective preventive measures that can be applied? Okay, so that's a good question, because first of all, it's about the land subsidence. It's actually the human-induced land subsidence. It's the only thing you can try to control. The sea level rise, we can try to control, but we have to do the whole world together, and we are depending because the sea, of course, is going everywhere. So I think that the most direct thing, and I think there are already steps being taken about that, is groundwater extraction. We all know that groundwater extraction is a big factor in land subsidence. So when you control the groundwater level, or you don't do excessive pumping, you will be able, at least in a local area, to control it a bit better. I think Jenny has shown you some pump data in the Bangkok area, and there it looks like the groundwater levels are increasing again, which is good news. Of course, there is sometimes a delay between the sand compaction from the previous pumping and how it responds. We will investigate that further. But it might very well be that there are other areas in Thailand where the groundwater pumping is still not as restricted or regulated. And in those areas, of course, you will get more land subsidence. So whenever any region you get the land subsidence, you cannot control it directly, but the government can by putting regulations in place for at least ensure that the groundwater levels are not affected. Another thing, of course, you can do if you're in a land subsidence area, in a coastal region, is that you also try to protect the land subsidence. This has been done also in the Netherlands by building dikes or mangrove forest recovery projects. You know, that these are ways you can at least try to defend. But the land subsidence, the only direct way we can look at that is probably the groundwater pumping. You know, of course, if you build a new area, that also has some effects bringing with it. You know? So you always have to be careful with the land development, taking this into consideration. So I hope that answers the question. One more coming. Okay. So is there any significant seasonal impact on land subsidence in each area interested? Well, actually, there is some. The groundwater, of course, is also changing. If there's a seasonal variation because you have a dry season where there's less rainfall, so the groundwater, the wells are a little bit are depleted more, and then the rain season comes, and there will be, and of course the sediment layer is also going to have impact to that. But I don't think that's the biggest worry, although it has some, but I think this is in the neighborhood. I don't know, I'm not the expert. From the GPS we can see sometimes, but then it's maybe 1 centimeter up and down, you know, depending in the seasonal. So that's not a big thing. Of course, if you have a storm and the land is a little bit lower, but I think these are details. The question, okay, but I think you have to more look at the long term and see what the changes there are and how they change from time to time.
Thank you very much, Mr. Wim Simons, for your kind answer. There is no further questions. All right. Okay, then we come to the end part of the seminar. Is there further questions? Okay, there is one more questions. Two questions. Okay, just wait for a moment. Two questions to Mr. Wim Simons again. Okay, please.
Okay, so I'll do my best, but if I think there is another expert still online, they are free, of course, to correct me. So let's try to see what the next question is. Do you have a dedicated test or a calibration area where you can compare all 4 techniques with each other over some longer period of time? I think that's actually also what Femke talked about at the beginning. We are still looking at all the data we have, and then we are looking for a number of locations. And then we are looking we're looking at where we have the GPS nearby or the GNSS results for a period of time, where we also have the groundwater information from the wells, and also where we have INSAR data. So we are trying to look at a number of areas. I think in the beginning we thought about maybe 3 or 4 in the Bangkok region, where we're going to try to compare all of those techniques together. So that's coming up in the next year. So good question, and exactly we're going to do that. And maybe later on we can extend to another area if we have, like for example in Samut Sakon, we have enough data, we can look in the later phase also there. So thanks. One more? Okay. So thanks a lot for your time and your attention also.
Thank you very much again, Mr. Wim Simons. Okay, right. Now we are at the end of the seminar, and we would like to say thank you to all the speakers and also to the audience for their active participations. Okay. The seminar has given us quite informative and interesting topics. Okay. And on behalf of the Council of Scientific and Technological Association of Thailand, I would like to say thank yous, and also to the other agencies that have cooperation from all the sectors and made such a good seminar like this to happen. And hopefully a good seminar like this will be organized again and again in the next future. And then it will be a benefit for the society and the nations, definitely. Thank you for your kind attention.